Welcome back, chemistry fans. Today we're going to do Unit 1, Topic 3, and we are going to be talking about significant figures. And significant figures are not like silhouettes of me or anything like that. No, that's just an impressive figure. That's not a silhouette. That's not a significant figure. A significant figure is actually a value that you have measured. So I'm going to try something off the cuff here and see if this works. I'm not sure it's going to, but we're going to find out here. So hold on. So what I'm going to do to start us off here is I'm going to do a little demonstration. So let's see if I can figure out, first off, how to do this. Let's get to my camera that I want here. Okay. So on my desktop here, what you are seeing are some different containers. This is a Erlenmeyer flask, and you notice its line only has the bottom line of 50 on it. Then I have something that's a little bit more accurate, and this is a beaker, and notice it has a 10 line on the bottom. And then this is your graduated cylinder, and it does also have a 10 on it. So quite the run of how we're going to measure. Let's see what the results are of it. And then I have this other graduated cylinder, and notice its 10 is at the top, and it has a whole bunch of lines to help me stay as accurate as possible. So what I'm going to do is I'm going to take just a simple container of water, and it is currently filled up somewhere in the neighborhood of about 150. Let me come down here to ground level. And you see there now, yeah, I'm somewhere in the neighborhood of about, actually 200. So what I'm going to try and do with this is I'm going to measure 10 milliliters so that it's a little bit easier for you to see and to distinguish which one it is. I'm going to put in a drop of food coloring so that we can represent which each one is from, green being the first one, red being the second one. Let's see here, and then, oh goodness, blue. We'll go with the third one here, and that's only a drop. That's not changing how I'm going to measure anything. And then I'll put the yellow in my last one, which is over here off the camera. But we'll save that one for the very end so we can make our comparisons. Okay, so what I'm going to do is I'm going to take my graduated cylinder here, and I'm going to see if I can guesstimate where 10 milliliters is. You could see my line of 50 there, and so I'm going to try and guesstimate that that's about 10 milliliters. Okay, put that off to the side. Now I've got a 10 milliliter line here in this beaker. I think it's going to be easier for me to hit 10 milliliters. So there I am. I stopped right at 10 milliliters. I think I'm pretty good on that one. And then finally here, my graduated cylinder, more opportunities because there's more lines. I'm going to turn this so I can actually see where I'm hitting it. Well, I actually went past it a little bit, but that's okay. It'll just exacerbate my point here a little bit. Maybe I can pour out just a hair so I'm a little closer to where, no, it's actually pretty close to it. Yeah, I'm pretty close. I'm satisfied with where I'm at with that one. Okay, so what I'm going to do next is I'm going to put this funnel into, you can't see this funnel. I'm going to put this funnel into each of the beakers that I have poured the 10 milliliters, and we're going to see just how close I am to actually 10 milliliters. So I pour it in, and what you'll notice is my line went somewhere past 10. So 10 is over here, and it looks like I'm easily 11. I went way past the 10 mark. So that was the best I could do with that estimation. All right, so now here is for the beaker that had a line on it. So I'm going to go ahead and pour it in. And what you'll notice, even with a line, I'm not too close. I'm at 9 point something. So I'm not quite up to my 10. So I still didn't do a great job. Now this one has the most lines of the three that we were pouring from. So I should get the best results. And well, I got better than I did with the other one, but I'm still a little bit shy of the 10. So that was probably my best effort right there as expected, but it didn't quite do it. Now, here's what I'm going to do for this final one is I'm going to pour it and show you with a graduated cylinder, more lines, how much better the scenario is, where I can stop exactly at 10. Yeah, I actually even went a little bit over, but that was my most accurate of all of my choices. So it did actually, without even practicing, it did exactly as I had hoped. It went from worst down to best, with the number of Sig Figs being that I had one Sig Fig, I had again one Sig Fig, maybe a better, and then I only had roughly one Sig Fig in each one of these, but I had more opportunities because it was a larger diameter that helped me at least guesstimate it a little bit better. And then finally I get to this one and it had two significant figures. So it did much, much better. All right, so now here I go. I'm going to get into the content where we can actually talk about what we need to know. So here we go with Unit 1, Topic 3. If you are following along, this is your Unit 1 notes packet. You scroll down and you would get into the Topic 3, and we're going to talk about those rules here in just a second. Most important thing we need to remember whenever we are measuring is that you must always estimate one more digit beyond what you had measured. Oh, let me change my screen here. There we go. And so now you always must measure one more digit beyond what you are certain of. So in this example here with the pencil, I know it's at least 6, and then I've got to make one more guess. Well, it looks like it's beyond halfway, so 6.7 would be the best guess. You can't say 6.75 because you don't have any lines to make it any more accurate. You always only estimate one more digit. If you put extra in there, you are violating significant figure rules. That's only when we are measuring. So now what we're going to do is we're going to move to the rules once we are calculating. So let me share with you the screen. Okay, here we go. All counting numbers are going to be significant if they give you a value. Now, if we're measuring, remember there's a different set of rules, but if these values are already given to you, any number that is countable, that's a 1, 2, 3, 4, 5, 6, 7, 8, 9, those are always going to be significant. They put those there because someone actually measured them. We don't do the estimation. We just assume that what is given to us is accurate. The problem is if there is one of the non-counting values, a 0. So if you have a 0 in the middle, in between counting values, you must count those zeros. If there is a real number in front and a real number at the end, there's zeros in the middle, those are significant. In this example, the 3 is significant, the zeros in the middle are significant, the 4 and the 2 are significant. But you must never count zeros in front. If there is no number in front that's a counting value, if it just starts with zeros, all of those zeros are insignificant. And for reasons that we will show you in the homework when we practice this, this could be turned into a scientific notation. This value could be 3.4 times 10 to the negative 5. On a similar note, but with counter examples, if there are zeros at the end of a value, they will always count. Zeros in front never count. Zeros at the end only count if there is a decimal. If you do not have a decimal at the end of your value, such as in the value down there, 190,000, all of those zeros are estimations. So you've got a couple of simple rules. Real numbers, always significant. Zeros in the middle, always significant. Zeros at the front, never significant. Zeros at the end are only significant if there is a decimal somewhere in the value. If you have no decimal, it is assumed that the zeros at the end are estimated. All right, now let's apply this into some example with multiplication, division, subtraction, addition. There are additional rules that we must be aware of for adding and subtracting. When you add and subtract, you only use the values after the decimal. If there are no values after the decimal, don't worry about it. Just add them together and use all the values. We only use significant number rules for adding and subtracting after the decimal. And what you must always do is use the lowest number of significant figures. You always use the lowest level of accuracy to apply to all of your values. So even though your calculator may spew out multiple decimals, you only use the lowest number from the problem, not the lowest value, the lowest number of significant figures. So if you notice in this first example, 83.2, it only has one significant figure after the decimal. 1.457 has three significant figures after the decimal. We can only use the one significant figure after the decimal. So my answer can only have one significant figure after the decimal. So that 84.657 rounds to 84.7. Same is true for a subtraction. The top value in the subtraction example has four significant figures. So I can only use four significant figures after the decimal. And you're saying, well, there's a zero in front. I get that. And that's a different set of rules. Remember this first slide that we talked about. This is how we count significant figures. This is how we add and subtract significant figures. So we don't discount the fact that there is a zero holding a place value. Sometimes these are called significant digits, not significant figures. We must be able to distinguish the rules for adding, subtracting, multiplying, dividing from the rules for just simply counting the number of significant figures. All right, when you multiply and divide, it does not matter where the values are. You only use the lowest number of significant figures. So in this example with multiplication and division, you do discount the zeros at the front. And I understand that this is going to be confusing, and that's why you practice, so that it doesn't become confusing. You have been utilizing significant figures for many years. It is time that you correctly apply them. Every single problem, there will be the expectation that you will use correct numbers of Sig Figs. You will get good at this by the end of the year. So in the first example, 4.36 has three significant figures. 0.00013 only has two significant figures. When I multiply it, I will only be allowed to use two significant figures in my answer. The zeros in front are not significant figures. And you're saying, but they were for the adding and subtracting. And I understand that that was adding and subtracting. This is multiplying, and it has a different rule. In the second example, there's a division problem. 12.300 has five significant figures. The zeros at the end are significant because there is a decimal. The 0.0230 only has three significant figures because the zeros in front are not significant. The zero at the end is significant because there is a decimal. I will only be allowed to use three significant figures. So that 534.7 rounds to 535. Okay, now this is an example that we are going to work together. So let me get myself to a tool that I can cut and place into the actual program that allows this. So we can manipulate and write on it. Try that again. There we go. Try this. Think, and I'm not sure why it did that. Let's try this again. It froze. Here it is. Okay. Now I've got density problem here. So in this density problem, I want you to recognize that density is a formula. Well, hold on. Before we even get to that, I need to inform you what the density formula is. Density is mass divided by volume. Now, if for some reason the problem asks you to solve for the mass given a density, well, you have this triangle, and you can manipulate this triangle knowing that anything on the bottom, it is multiplied together. Anything on the top is divided by the value down below. So it'd be mass divided by density gives you volume. Or if we wanted to solve for a density, well, remember, mass divided by volume equals density. If you wanted to solve for the mass, what you simply do is take two numbers down below and you multiply them together. Now, in this slide, you notice that I have gone ahead and simplified all those for you as well. Now, I did not share my screen while that was going on, I believe. So hopefully now we can get that done. Share my screen about what I was just working on there. So in this problem, that is your density triangle. Mass divided by density equals volume, or mass divided by volume equals density. And if I wanted to calculate what is the mass, I would simply multiply d times v. And again, if you need that written out, that's a way for you to memorize it. But if you can't memorize that density formula, the triangle, you are certainly welcome to utilize just rote memorization. D equals m over v. D equals m over v. And in this case, mass equals d times v. Okay, now let's go back to the example problem. So let's see here. In these example problems, we are going to be working with density, and I want us to apply significant figures. So we are given milliliters. You're going to have to understand that milliliters is a volume. You're going to have to recognize that unit. Milliliters are volume. It's asking for the mass, which is the weight, and they give us a density. The density is grams, which is a mass, divided by milliliters, which is a volume. That's D equals M over V. Okay, so we know the formula. D equals M over V. We are asked to solve for what is the mass. Now, again, I could use algebra and solve for that value. Or I could look at my triangle. M is equal to D times V. And if I'm looking for mass, that means that I'm going to multiply D times V. All right, so I have a volume. That's 200 milliliters. And let's use significant figures. 200.0 milliliters multiplied by 0.789 grams per milliliter. Now, the first thing I want you to notice, when I multiply, I've got 2 milliliters. There's one on top and there's one on bottom. They are going to cancel out and give me the unit that I desire, which is grams for a mass. Next thing I want you to notice, how many Sig Figs do I have? 1, 2, 3, 4. 4 Sig Figs in the first value, 1, 2, 3 in the second value. Zeros at front do not count as significant. The 0 in the first 200.0 does count because there is a decimal. Now, I'm only allowed to use 3 significant figures. So don't cut off your significant figures while you're calculating. Plug them all into your calculator, 200.0 times 0.789. And what I end up with is my answer, which is 157.8 grams. But I'm only allowed to use 3 significant figures. So this 8 is going to round up that 7. My final answer is going to be 158 grams. No decimal point needed. It's understood that counting numbers are significant. I don't need to include a second significant figure in that value. Okay, next. I've got a rectangular block. In other words, it's a cube. Rectangular block of copper metal. It weighs. So I've got a mass here. The blocks are 8.4 by 5.5 by 4.6. Now, what that means is I've got this cube, and it's got 3 different dimensions: length, width, and height. So all I got to do is just multiply them all 3 together. Volume is equal to length times width times height. So I will take 8.4, you can't see that, 8.4 times 5.5 times 4.6. All of those have 2 significant figures, but I don't apply significant figures until the very last step. So I will take my 8.4 times 5.5 times 4.6. So even though I'm only allowed to use two significant figures, I'm not done with my calculations. So I do not change them. Now, here's another little trick. This is the first time I'm going to mention it, not the last time. Centimeter cubed is the same thing as a milliliter. So my answer right now is 212.52 milliliters. That's my volume. My mass is equal to 1896. Density, if you remember, is equal to mass over volume. So I've got 1896 divided by 212.52. So I plug that into my calculator, 1896 divided by 112.52. And what I get is a whopping 8.9215, blah, 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 blah. I'm just going to drag out those numbers. And now we can apply Sig Figs. There are two significant figures in each of these values. There are 1, 2, 3, 4 in this value. I'm only allowed to manipulate it twice. So I'm only going to use two significant figures right here. My answer is 8.9 grams per milliliter as the density. Okay. I've demonstrated significant figures. I've instituted it inside of a concept called density, which you are familiar with. D is equal to mass over volume. I hope that you have a better understanding of what significant figures are, why they're important, how to utilize them. Thank you so much. I will talk with you again soon. Farewell. Bye.